All right, everybody, welcome back to the Science Channel. Today we're going to be doing a quick video on basic thermodynamics. Hope you enjoy. Now we all know that water melts or freezes at 32 degrees Fahrenheit or 0 Celsius, and it boils at 212 degrees Fahrenheit or 100 degrees Celsius. But here's my question for you today. If I have a bowl of ice water, which is to say water with ice mixed in it, and I leave it on the counter for 5, 10, 20 minutes, do I know what the exact temperature is? Let's find out. All right, so I have my water from the tap here, and let's see what the temperature is. 66 degrees Fahrenheit. That's cool water. Now, I'm gonna go ahead and throw some ice in there, and let's see what happens. It cools, of course, but to what temperature? I'll tell you without looking that as soon as the temperature stabilizes, provided that there's any ice left after melting, the temperature will be exactly 32 degrees. And it will remain that exact temperature no matter how long it sits, as long as the ice remains. So as it cools, let me explain. And by the way, since I have this cool magnetic stirring machine, I'm just gonna turn this on a little bit. And that's just gonna help stabilize the temperature of the water quicker. The reason behind this is basic thermodynamics. There's a material property called the latent heat of fusion. And what this property measures is how much energy it takes to cause a state change. So we have, in general, 3 states of matter: solid, liquid, and gas. So the latent heat of fusion tells you how much energy you need to put into a substance to get it to either melt or freeze. So we're changing the state of something from a solid to a liquid, or vice versa. It's the same amount of energy each way. For water, this amount of energy is 334 joules per gram. Now that means to change the state of water from solid to liquid, to go from ice to water, you need to supply 334 joules of energy per gram of ice. If you want to go the other way, to change from liquid to solid, this is freezing, you need to remove 334 joules of energy per gram of water. And this is what happens in your freezer when you make ice. So what's happening in the bowl is this. I have water from the tap. Now under normal conditions, I don't know what the exact temperature of that water is. All I know is that it's liquid, so it must be somewhere between 32 degrees Fahrenheit and 212 degrees Fahrenheit. Now as I add the ice, which, by the way, I don't know the temperature of either, I just know that since it's solid, under normal conditions, it must be 32 degrees or less. So I add the ice to this water, and then the molecules start to mix. Now as the molecules interact with each other, and basically what they're doing is they're just bumping into each other very quickly, the warm water is transferring some of its energy to the colder ice. This has the net effect of cooling the ice water solution. Now one of 2 things is going to happen here. The first, it's possible that I don't have enough ice, or the water was initially too warm and there wasn't enough ice to cool the water to 32 degrees. And that would mean that all the ice would go away and the water would be somewhere above 32 degrees. It'd be cooler than when it started, but it didn't reach 32 degrees. This is what happens, of course, when we just put some ice cubes from the freezer into our water to make it cooler. Now, the second thing that could happen is that the water cools to 32 degrees and there's still some ice left. What happens now? So if ice still remains in the ice water solution when the water is 32 degrees, then that means that the temperature will not change until all the ice is melted. What's happening here is that all of the energy that was going into cooling the water down to 32 degrees now goes purely into melting the ice. The temperature will not dip below 32 degrees. So all of that energy, all of the additional energy is going into that phase change that I mentioned before. And so you can calculate the exact amount of energy that I have to add to melt the rest of the ice by knowing the latent heat of fusion, which I mentioned before, 334 joules per gram, and the weight of the ice that I have. Now at this point, you'll probably notice that the thermometer is stuck at 32.4, 32.5 degrees, and it's staying there. And you wonder if I lied to you, because I said that the temperature is exactly 32 degrees and that it cannot go below 32 degrees because all the energy is going into this phase change of the ice rather than cooling the water. But why is it exactly 32 degrees? So it turns out that this thermometer has an accuracy of plus or minus 1 degrees. So it could be 1 degree off in either direction. The thermometer isn't positive. If it reads 32.5, it could be 33.5 or 31.5. This is a limitation of the tool, not a problem with the science. Okay, let's try another experiment to see if we can extend this concept. So here I have a pot of water that I'm going to boil on the stove. I have the same tap water, and I'm just going to boil it using my gas stove here. Let's see what happens. Now, of course, we know, like we mentioned before, that water boils at 212 degrees Fahrenheit. So when the water is clearly boiling, that's the temperature we expect to see. But now my question to you is, what happens when I turn up the heat? What happens when I turn up the heat and leave it on for 5 minutes? What's the temperature then? Well, if you understood the last example, the same exact principle applies. The temperature remains at 212 degrees Fahrenheit. That's because all of the energy that I'm adding is no longer going into increasing the temperature of the water. It's going into the phase change, in this case, liquid to gas or liquid to steam. But wait a second, something strange is happening here. We all know, and I told you before, that water boils at 212 degrees Fahrenheit. So why is the water obviously boiling even though the thermometers are reading less than that? What could it be? I'm not gonna lie to you, when I was doing this experiment, I was stumped for a second myself, and I didn't know, is something else going on here? Are the thermometers wrong? And just at the point where I was questioning my own sanity and scientific knowledge, I remembered something. I remembered where I live. So I live in the mountains. And here it is. As atmospheric pressure decreases, water boils at lower temperatures. At sea level, water boils at 212 degrees Fahrenheit. That's what we expected. But with each 500 feet increase in elevation, the boiling point of water is lowered by just under 1 degrees Fahrenheit. At 7,500 feet, for example, water boils at 198 degrees Fahrenheit. So that explains why our temperature reading was lower and why the water was indeed boiling at that temperature. Well, I gotta admit, that was a Scooby-Doo mystery for a minute there. Thank God we solved it. So I thought I was gonna have to delete this video, return my engineering degree. It was gonna be very embarrassing for me. So small tangent here. What's actually happening is that the air around us is exerting a certain amount of pressure. We don't think of it because it's all around us, pressing us from all sides at all times, and so it feels like nothing, but there is in fact a pressure, and it's called atmospheric pressure. And that pressure is literally the weight of the air on you at all times. And so what happens is that as you get higher up in altitude, there's less air above you to push on you, and so there's less atmospheric pressure. This is why it's harder to breathe at higher altitudes and things like that. And so for our water that we're trying to boil, there's downward pressure trying to keep the water in the pot there, keep it from escaping. And then as we're heating it, we're providing it with energy to try to escape the pot. And so when we give enough energy and it can escape, that's when it boils off. But if there's less atmospheric pressure, well, of course, that's going to require less energy to be released. And so that is why the boiling point decreases with altitude. So to illustrate this concept in graphical form, I have this picture from Wikipedia, this graph. So what do we have? On the y-axis, we have the temperature of the water. And we have degrees Celsius, so we're in metric units now, doesn't matter. And on the x-axis here, we have heat added. Now we start here at the bottom left. This is the temperature of the water, negative 100 degrees C, very, very cold. So this is pure ice, very cold. And we start to add heat. Maybe we put it in a hot room, maybe we put it on a flame. And so as we add heat here, the temperature of the ice rises. And it rises and it rises until it reaches 0 degrees Celsius. This is the melting point. Now what we're seeing here is that as we add heat, which is as we travel to the right on this graph, the temperature of the ice does not change. It just melts. So we have here melting ice, ice plus water. And this latent heat of fusion, this is what I was talking about before, the amount that you're adding is 334 kilojoules per kilogram. Another way to say that is 334 joules per gram. It's the same thing. So as I add heat here, it's not raising the temperature anymore. It's only melting the ice. It's only changing the state of the ice. Now, once I add enough heat to this ice water, at some point, all the ice melts, and now it's just pure water at 0 degrees. And now, when I add more heat, I'm starting to move up this line to the right. I'm adding more heat, and the temperature of my water is rising until it gets to where? Until it gets to 100 degrees. This is the boiling point of water. So now the water starts to boil, and the same process occurs. As I add more heat, which is going to the right on this graph, you'll notice that the temperature of this boiling water does not change. It's still 100 degrees. So all the energy that I'm adding is only boiling the water. It's changing the state from liquid to gas, from water to steam. And you'll notice, by the way, that this latent heat of vaporization is much larger in magnitude than the latent heat of fusion. It's about 7 times larger. So where it was 334 kilojoules per kilogram or joules per gram, they mean the same thing. Now we have 2,265 kilojoules per kilogram or joules per gram. So it takes a lot more energy to change the state of water from liquid to gas than it does from solid to liquid. Now, once all of that water is boiled away, once all the water is gone, now we have just steam left, there's no more water left. And as I add more heat, now I can raise the temperature of that steam again. And that's what you see here. So the next time you're cooking, here's what I want you to do. Go ahead and boil that water. Turn the heat up as high as you want on your stove to get to boil quickly. But once the water starts to boil, you know the temperature. It's 212 degrees. At that point, go ahead and turn the temperature down until the water is just simmering. It's still boiling. It's still 212 degrees, but you're saving energy. Because if you were to keep the stove at the same temperature or even turn it higher, you're not increasing the temperature at all. You're only boiling the water away faster. So go ahead and turn the heat down, simmer it instead, and you'll save some energy. Okay, there we have it. Learning a little bit about thermodynamics. That's our improvement for today. As always, thanks for watching. See you next time.